Good morning, all. This is the continuation of our last class on Module 3 Electronics. That was class 2, and now this is class 3. So, in the last class, we have studied about two definitions, right? Drift current and diffusion current. Then we studied about what is biasing, the various types of biasing, the characteristics, and schematic representations of both types of biasing. Okay, now in today's session, we will see how current flow in a forward bias PN junction. So we know what forward biasing is. That is when once a PN junction is formed, if the P region is connected to positive terminal of battery and N region is connected to negative terminal of battery, we call it as a forward biased PN junction. So when a PN junction is forward biased, first of all what happens is that the electrons, that is the majority charge carriers of N region, that is electrons, will move towards the junction, leaving behind positively charged atoms. So there will be a deficiency of electron, and that vacancy will be filled up by another electron that enter into N region from negative terminal of battery. So once an electron move from N to P region, that vacancy is filled by another electron that enter into N region from negative terminal of battery. So this loss of electrons is continuously replenished. Now this electron will move towards the junction as free electrons, and at junction they will combine with holes and will become valence electrons. Now these valence electrons will move through the P region, and when they reach the extreme left end of P region, they will enter into the positive terminal of battery. So here you can see a continuous flow of electrons outside the circuit. Okay, this is how current flow in a forward bias PN junction, that is an electron going to the junction from N to the junction. So an electron enter from negative terminal of battery, it moved through the PN junction, and then it enter into positive terminal of battery. So the electron flow will be like this. So this is the mechanism of current flow in a forward bias PN junction, and it is well described in this paragraph. You can go through it. Okay, next, this is the important session topic for today. VI characteristics, and that is current voltage characteristics. It is nothing but a graph showing the relation between current through the diode and bias voltage. That is, current through the diode I is plotted at on y-axis, and the bias voltage V is plotted along x-axis. So that graph is called the VI characteristics of the diode. Now this is actually the circuit diagram for drawing the VI characteristics of a diode. See, you have a battery here, then a rheostat, voltmeter, a PN junction diode, then again you have this is a key, a resistance, and a millimeter. Okay, so this is the experimental setup, and after doing this experiment you will get a graph as shown. This is called the VI characteristics of a diode. This graph is very important. See, voltage, bias voltage is plotted along x-axis, and current is plotted along y-axis. This is stands for forward voltage. Here we plot forward current, here we plot reverse current and reverse voltage. So this one stands for forward characteristics, and this one stands for reverse characteristics. So both these two combined will give you VI characteristics of the diode. Now here, how you get, I will explain how you get this particular part. Similarly will be the other part, so just one I will explain. See here, by adjusting rheostat, you will keep slowly increase this bias voltage using this rheostat. So you note the voltmeter reading as 0.1, then the corresponding millimeter reading you will note here. Again we adjust the rheostat and keep the voltage at 0.2 volt, then you note the millimeter reading, that is current value. So you get voltage to plot along x-axis and current values to plot along y-axis. This is how you obtain this graph practically. Okay, now we will study this graph in detail. So while drawing the graph, you have to explain each of this. What is VR, what is IF, what is VF, what is IR, and all. It is described here. So now we'll study this graph. For that we study it under three bias voltages, namely zero external voltage, then forward bias and reverse bias. First of all, we'll see zero external voltage. Zero external voltage means potential barrier does not permit current to flow through the diode. That is, when external voltage is 0, potential barrier does not allow current to flow through the diode, and it is represented by the point 0 shown in this figure or shown in this graph. Next we will see forward bias. You know what is forward biasing? That is P region connected to positive terminal of battery and N region connected to negative terminal of the battery. So once PN junction is forward biased, in the last class we have studied about the characteristics. What are they? Potential barrier decreases, depletion layer decreases, so majority charge carriers easily cross across the junction, resulting in the flow of a current called forward current, and this current increases with forward bias voltage, right? So similarly you can see what I will brief what is told in this paragraph. See the figure here. First of all, we are increasing the bias voltage, I mean forward bias voltage, from a small value, say 0, and we are slightly increasing it. So once bias voltage increases, forward current also increases, and that portion is represented by OA. A small increase in forward bias results in a small increase in forward current, and this increase is actually non-linear. Why? Because potential barrier, that is a strong, we have to see here this OA, this that curve is non-linear, but after a particular point, say A, what happens? Forward current increases to a very large value with increasing bias voltage, and that region OA is curve that is linear. So this full curve, that is the curve OAB, is called forward characteristics of the diode. So from O to A, that particular curve is non-linear, whereas from A to B it is linear. That is, with small increase in bias voltage, forward current increases, but after a particular point, say A, forward current increases to a very large value with increasing bias voltage. So that particular point A is called knee voltage. So knee voltage is nothing but the particular value of forward voltage across the PN junction at which forward current increases rapidly. Please note down this definition. The particular value of forward voltage across the PN junction at which forward current increases rapidly. This is the definition for knee voltage. For silicon it is 0.7 volt, and for germanium it is 0.3 electron volt. It will be discussed later. So here this is why you have already said that up to this point OA the curve is non-linear. Why? Because the applied voltage has to overcome the potential barrier. Once the applied voltage overcome potential barrier, forward current increases rapidly with the bias voltage. Now let us see the reverse biasing section. What is reverse biasing? The N region connected to positive terminal of battery and P region connected to negative terminal of battery. Okay, so what are the characteristics? Depletion region widens, that is potential barrier becomes high, practically no current flows, but a small current flow due to the flow of minority charge carriers, and it is called reverse current or leakage current, that we have already discussed. So in this reverse biasing case, see what happens here. This is the region. We are slowly increasing reverse bias voltage, so reverse current also increases, and after a particular point is say C, it increases rapidly but in this negative direction. So here at this particular point O, the particular value, that is O, is called breakdown voltage. So breakdown voltage is nothing but the particular value of reverse voltage across the PN junction at which reverse current increases rapidly. So note that also. Breakdown voltage is defined as the particular value of reverse voltage across the PN junction at which reverse current increases rapidly. Okay, so these two are the definitions. So here we can say one or two points here in reverse biasing. Okay, so that region is represented by OC in the diagram. Just refer to the figure also. If reverse bias is increased continuously, what happens? Kinetic energy of electrons increases. That is, their energy increases, and this energized electrons will knock out electrons from the atoms of semiconductor, and this results in sudden fall of resistance of barrier and a rise in reverse. And this paragraph actually explains how or the mechanism behind the sudden increase in reverse current. Now, so the reverse voltage required to required to occur breakdown of the region is called breakdown. This is also another definition. You can choose any of these definitions, and it is represented by the point C in the graph. I have already told you that is called breakdown voltage. Okay, now these are the definitions. It is a breakdown voltage is a minimum reverse voltage at which PN junction breaks down with a sudden rise in reverse current. So, in order to prevent the breakdown of junction, what should we do? The reverse voltage that we are applying must be always less than breakdown voltage. Now, this is the definition for knee voltage. For silicon, it is 0.7 volt, and for germany, it is 0.3 volt. So, you can study either these definitions or the definitions that I have told before. Once again, I tell knee voltage is a particular value of forward voltage across the PN junction at which forward current increases rapidly, whereas breakdown voltage is the particular value of reverse voltage across the PN junction at which reverse current increases rapidly. So, you can write either these definitions or these two definitions shown here. Now, the last session for today is about Zener diode. Zener diode is nothing but a reverse biased operated diode. That is, it is designed to operate under reverse bias in the breakdown region and used as voltage regulator. This is the schematic diagram for a Zener diode. And here, this is a P region, the arrow part. The other one is a negative part, that is cathode. So, anode, and this is the anode and cathode. Okay. Now, the Zener diode is heavily doped. Its depletion region is very thin. Electric field is also at the junction is very high. You can write these values if you remember, or else you just brief the points. Okay. Now, about IV characteristics of Zener diode. This is a VI characteristic. So, voltage along x-axis and current along y-axis. Now, when reverse bias voltage, that is V, reaches breakdown voltage Vz of Zener diode, there is a large change in current. Current increases, but there will be insignificant change in reverse bias. There will definitely be a change in current. In other words, Zener voltage, that is Vz, remains constant even though current through the Zener diode varies. So even though current across the Zener diode varies, the Zener voltage remains constant, and this property is used in the manufacturing of regulated power supply. So the Zener diode is used as rectifier and also as a voltage regulator because it has this property. Which property? Its voltage remains constant even though current through it varies over a wide range. So study this also. Zener characteristics is also important. Now, the mechanism behind the sudden increase of reverse current at breakdown voltage is that when reverse bias voltage is increased, electric field becomes significant. Just note the underlined portions. Then, electric field strength is high enough to pull valence electrons, and this naturally results in the high value of current observed at breakdown. So, that's a reason. That is, when reverse bias voltage is increased, electric field becomes significant. Then, electric field strength is high enough to pull valence electrons. This will result in the high value of current observed at breakdown region. Now, study this definition, that is, the emission of electrons from the host atoms due to high electric field is known as internal field emission or field ionization, and its value is 10 raised to 6 volt per meter. So, I think that's all for today. So, here in today's class, the most important topics are for the what is VI characteristics and the circuit diagram, then the VI characteristics, that particular graph, and then analysis of that graph under three conditions, which are they: zero external voltage, forward bias, and reverse. It is very important, so study well for your exams. Also, Zener diode, how it can be used as a voltage regulator, its symbol, what is it, and its characteristics. Okay, that's all for now. Okay, thank you.